and then very, very thin by the end. So that's one of the coolest maps out there, I think.
Oh, that's really cool. But yeah, we'll let Brendan get started. And just a reminder to everyone to please hold on to your questions until the end. We'll have some time for questions then. But yeah, thank you so much, Brendan, and excited to hear what you have to say.
Yeah, thanks, Rachel, and thanks to everyone for being here and for PYRN for inviting me here. Uh, so today, Rachel kind of laid out the different things I've done, and I'll kind of go through it chronologically as well as topically. So I'm going to present kind of my origin story, which is mainly based on field research in the Western Arctic, a little bit about the postdoc I did in Svalbard about ground ice conditions, and then research from my current job at the Geological Survey of Canada. And I'll talk a little bit about field aspects involving thaw subsidence measurements. And then a lot of the talk will be focused on ground ice modeling and what I'm currently working on. So my master's research was with Chris Byrne, and it took place at Ilisarvik in the very northwest corner of Canada. And some of you may have heard of it. It's a drained lake basin that was drained in 1978 by Dr. Ross Mackay to study the growth of permafrost into a talc, essentially. And it's been the site of a lot of permafrost research in Canada for decades, since it was drained in 1978 and even a little bit before that. The landscape here, a theme throughout this talk will be kind of understanding the landscape and how the history of the landscape and how that influences ground ice conditions. So the landscape here, you can see it's kind of rolling hilly terrain, not super tall hills, and there's a thin veneer of silty glacial till overlying a thick sequence of sands. So I just wanted to give that context because it kind of provides useful information moving forward. And in the lake basins, these drained lake basins, like by the red dot, which is Lake Ilisarvik or used to be, there are lacustrine deposits, so fine-grained deposits that have a bit more organic material in them as well. So here's a picture of the Ilisarvik drained lake basin from my master's in 2010. And my master's really focused on trying to figure out how much ground ice had formed in the basin sediments since drainage in 1978. And in particular, how much segregated ground ice. So, ice lens type of ground ice. So we drilled a lot of cores in the lake basin, I think 26. And then we contrasted this with the conditions in the tundra, which obviously is a much older environment and also different sediments. And what we found was in the basin, we found excess ice up to 60 centimeters below the permafrost table as of 2010. And in the basin at ice-rich sites, there was about 8% excess ice content in the top 50 centimeters. Now, for those unfamiliar, excess ice is the amount of ice in excess of the soil's pore space when that soil is thawed. So if you thaw soil that has excess ice, you expect subsidence. And in the tundra sites, which are this bottom graph, on the x-axis here, we have excess ice content, and on the y, we have depth below the permafrost table. There's much more excess ice in the tundra, about 25% in the top 50 meters of permafrost. And what we also did was compare the amount of excess ice that accumulated with changes in benchmark protrusions in the basin. And because as the segregated ground ice grows in the top of permafrost, the ground surface heaves upwards, and then the benchmark protrusion decreases because the benchmark's anchored in permafrost and the ground surface rises as the ground ice grows. And we found that the excess ice growth corresponded from our coring corresponded to long-term heave at the benchmarks, which was nice to see. And the final thing that I'll just point out is this really allowed me to think about the importance of time and the history of the landscape in how much ground ice you might expect to see and what types of ground ice you expect to see. So what I plotted in my master's thesis was different studies looking at segregated ice accumulation in known intervals. And you can see there's kind of this, the longer time period you have, the less ice accumulation rate in millimeters per year. And that's because you have fluctuations in the active layer, melting and reforming of segregated ice. So over 1 year, you can have quite a bit of ice formed. But if you average it out in a natural setting, that rate declines if you're looking at how much ice forms per year. So next I'll take us to Peel Plateau, which is the site of my PhD that I also did with Chris Byrne. And this was more on thermal conditions than ground ice conditions, but I learned about thermal conditions, or sorry, about ground ice conditions while doing this study. And so this image shows the Peel Plateau. On the left side are kind of the foothills or Richardson Mountains, so essentially exposed bedrock. And then the plateau itself, which is between the left side and the river, is this upland of thick glacial sediments that accumulated near the edge of the Laurentide ice sheet during the last ice age. And this stuff is full of buried glacier ice. And you can see that we have these gully systems that cut across Peel Plateau and drain downslope towards Peel River. And that erosion exposes or can expose these very ice-rich sediments and cause massive retrogressive thaw slumps, like this one shown here. Uh, so the head wall of this is essentially pure buried glacier ice. It looks very dirty, but that's just because there's sediment and muck that kind of runs over it from above. But it's essentially quite pure ice. And this occurs under these fine-grained tills that also include segregated ice. What you might notice is that we don't really see wedge ice in this exposure, and that's something we'll talk about, which my PhD work on the thermal conditions kind of help figure out why we don't see much wedge ice here. So my PhD focused on looking at the permafrost conditions and comparing those in the lowlands around Fort McPherson, so in the Peel Plain at low elevation, to conditions on Peel Plateau itself at higher elevation. And what we found is there are very strong winter air temperature inversions that take place between the plain and Peel Plateau. So as you move up in elevation, you actually get much warmer air temperatures, particularly in very cold snaps during winter. So the graph at the top left shows air temperature plots. One is at 30 meters near Fort McPherson. One is at 492 meters on Peel Plateau. And then the one just below it in panel B shows these inversion lapse rates. So the difference between air temperatures across this elevational gradient. And resultingly, what we saw in the ground temperatures, so the bottom left shows elevation and the temperature, the annual mean temperature near the top of permafrost, so at about a meter. And what we see is that at most tundra sites, the ground temperature is actually warmer than in the lowlands near Fort McPherson. And that's partly because we have these very strong temperature inversions. So the winter climate on the plateau itself is much warmer. And we see that reflected also in deeper temperature profiles. So on the right, you have depth on the y-axis, temperature on the x, and the lowland spruce forest site, so the one at 30 meters, is colder even than the dwarf shrub tundra site at the highest elevation, and much colder than the upland spruce forest site at lower elevation, but on Peel Plateau. So what does this mean for ground ice? Well, these two plots show ground temperatures from shallow thermistor sites at 4 depths, so 5 centimeters up to 1 meter. And these are from two sort of contrasting peatland sites. The first site has a lot of snow accumulation, and what you can see in this plot is that the active layer does not freeze back until mid-April. So that's a very late freeze back, and consequently, the ground temperatures stay very warm. Even after freeze back, they don't go below -5. Now, the one below in B, which is dwarf shrub tundra peatland, is about the coldest site you can expect on Peel Plateau. It's very flat, though there's not much snow that accumulates because it blows away off the flat surface. And even at this site, the ground temperatures we get are marginal for thermal contraction cracking. And this was in 2011. So now we know there's lots of warming going on in the winter. These ground temperatures are probably in general warmer than they were when I did my PhD. So really, we don't have the conditions for much thermal contraction cracking and ice wedge accumulation presently on Peel Plateau. And there's only ice wedges on Peel Plateau in these small peatlands that are flat. And these ice wedges probably formed in the past when the ground when the ground climate was colder. So that's one of the reasons we don't see many ice wedges in exposures of slumps on Peel Plateau. It just isn't cold enough consistently to form ice wedges over a widespread area. So now I'll jump outside of Canada to Svalbard, which is where I did a postdoc with Dr. Hannah Christensen. And this also kind of really, this image kind of hammers home the diversity of landscapes you can have and how that might influence ground ice content. So you can see in the uplands is kind of weathered bedrock. There's colluviation of pretty coarse material flowing down those slopes. You have these beautiful alluvial fans coming out of the river valleys here. And then bounding the main braided river channel valley, you have aeolian sediment that's accumulated during the Holocene when big windstorms blow down this valley. So there's a lot of complexity going on in the geomorphology, and a lot of differences in the texture, the soil texture you have. And so expectedly, you would think, well, we're probably going to have different ground ice conditions. So one of the things I wanted to look at in my postdoc, which really didn't work out because the fall that I was there was it was an incredibly wet fall. The places I wanted to drill were all flooded because there was so much rainfall. So we ended up drilling kind of later the next spring when everything was still frozen. And consequently, I didn't get as many cores as I wanted to. And that's just research. Sometimes you don't get what you want. But I showed this picture because it shows these very nice polygons here. This is not where I drilled, but it's much more photogenic than where I drilled. So I added this picture. And I also thought it was neat that this place is called Revnese, and in Norwegian, this means cracked. So it's named after the ice wedge cracking. So what I did manage to do was I drilled 8 cores within 2 different ice wedge polygons that had different morphology. And I really wanted to get at like what is the site scale variation that we get in segregated ice content, uh, so that like we would know how representative any given if you only took 1 core somewhere, well, how representative is that of this polygon field? So I managed to drill 8 cores, and finally I ended up writing up this data and publishing it as a GSC open file. But interestingly, between these 2 polygons, which are only like not very far apart, about 70 or 100 and something meters apart, they had drastically different segregated ground ice contents. And the reason for that is in the past, this these polygons grew on a grading aeolian terrace. And in the past, the deposition, even just between this one polygon and the next, differed significantly. One of the polygons had much more fine-grained silty material at depth than the other one. So consequently, the one with the siltier, more frost-susceptible material had about double the excess ice content of this other polygon. So it goes to show you, if you go somewhere and you drill 1 borehole and you think you've got a representative sample of maybe that small terrain unit, it's not necessarily the case. I was also lucky to be involved in Graham Gilbert's PhD research, which involved drilling much deeper. So this is the UNIS custom drill rig called Boring Betty, but she's not boring. She's quite exciting, as you can see. And this drill allowed us to go down 20 meters and get basically completely intact cores of permafrost. And so this was for Graham's PhD thesis, which was examining more like landscape development type stuff and ground ice conditions in different stratigraphic units. So detailed lab analyses were done on all of these on three 20-meter cores, and then Graham also had a 50-meter core that was obtained from an industrial drill rig, which is amazing because that core reached through the full sedimentary like package down to basal hill. So Graham was able to reconstruct the landscape development in this fjord valley since deglaciation, which is shown here. So yeah, being on Svalbard taught me kind of two things was, okay, we can't take what we have in one or two boreholes as an estimate of even a small landscape unit. And also, uh, it gave me an appreciation for this longer term landscape development and the ground ice conditions you can expect in different layers and in different permafrost types. So whether you have uh, syngenetic permafrost or epigenetic permafrost, where you can expect the ground ice in those settings. And Graham also taught me that making figures in CorelDRAW is really fun, and he makes really nice figures in CorelDRAW. And when I was in Svalbard, if you ever get the chance to go somewhere new and do research, take that chance because you'll meet a lot of new friends and get to experience the local cuisine. So now I'll jump to the Geological Survey of Canada and some field-based research that we did recently. Well, I started this looking at the data from thaw tubes in about 2018, but we only published it in 2023. So a thaw tube is a quite a simple instrument that allows us to see three things. One is the thaw penetration, so the annual thaw penetration, but also the overall thaw penetration with respect to a fixed datum, which is the reference height, because these thaw tubes are anchored about 4 meters deep in permafrost. Now, some have become unstable because of significant permafrost degradation, but most remain stable. We chuck those out from our analysis. And then on the right side, you'll see the network of thaw tubes that we at the Geological Survey are lucky to have. These were installed by Mark Nixon in the early 1990s. And so we have like 3 decades of measurements of thaw penetration into permafrost, active layer depth, and ground surface subsidence, because the instrument allows us to measure the position of the ground surface as well. And what we saw from this long-term monitoring research is that, as we'd expect with climate change, thaw penetration has basically increased at most sites. So on the top pane of the graph, you can see all the sites plotted, the time series of thaw penetration, and then the thick line is the average. And we also see basically at every single site, the ground surface elevation has decreased. So we're having the thaw consolidation, so the melt of excess ice or consolidation of thawed sediments happening. And the active layer thickness plot shows that, well, the trend isn't as easily discernible as it is in thaw penetration. And this is because the active layer thickness is being measured from the ground surface, and the ground surface is generally moving downwards. So we basically underestimate the permafrost thaw if we measure active layer thickness in areas where there's subsidence taking place. So this map shows the same data I just showed on the last slide, but in a different format. And these circles, the size of the circle is proportional to the slope of the regression put through the time series from each site. So basically the rate in centimeters per year of change in thaw penetration, ground surface elevation, and active layer thickness. And what we see again is that, basically almost everywhere we have increasing thaw penetration, and we have a sinking down of the ground surface elevation. And that the sinking of the ground surface elevation depends a lot on local conditions and how much ground ice you have in the ground. And then, but an active layer, the story's not so simple. Some sites, the active layer has thinned, uh, even as the thaw penetration has increased. So what this again shows is that measuring active layer is actually not great for capturing the degradation of ice-rich permafrost. And this kind of reiterates that. So on the left, we have plotted thaw penetration versus active layer thickness at all the sites in every year at a one-to-one line. And so all the dots below the one-to-one line basically show that we're underestimating permafrost thaw with an active layer measurement. What we also saw that was cool with thaw tubes was we were able to see aggradational ice growth. So 1998 was a year of very deep thaw in the northwestern Canada, but subsequently there were some years that were cooler than that year, and so the permafrost table aggraded, and in association with that, the ground surface elevation increased. So we had the growth of segregated ice, and that's what the plot on the top right shows. And then I was able to, well, I just did this for this presentation, but sort of add these rates of ice growth to this graph I made for my master's thesis. So again, you can kind of see this relation between ice accumulation and the period of accumulation for segregated ice. So I want to now take an interlude and just highlight the importance of process and field knowledge when you plan to do modeling. So if you have good knowledge of the processes that are occurring in permafrost regions and field knowledge of the areas you're modeling, you will undoubtedly create a more useful and better model. Um, I review a lot of papers where it's strictly a modeling exercise. It could be, a machine learning method inputting different parameters to try to predict something. Uh, and a lot of the time, these parameters don't actually relate to the physics that are going on in terms of ground ice accumulation or melt or any other periglacial process. So I just want to highlight, like, as much as you can, learn about the area you're studying before you start to model it. And this example is from the Great Plain of the Kuujjuaq on southwest Baffin Island. And a lot if you have no knowledge of this area, you might look at this and say, "Oh, that's weird. There's a lot of round lakes. I don't know what's going on." But if you dig deep into existing literature and resources like surficial geology mapping, you will learn a lot about the area that will help you understand ground ice. So one is these are glacial marine sediments, and this area was underwater until very recently, because after the ice uh, receded in this area during deglaciation, there was isostatic uplift, and so this is an emerged landscape. That sediment is very fine grained and it's very frost susceptible. So what we have in the near surface, or at least, I mean, I haven't drilled it, but this is what I expect, is that we have quite a bit of segregated ice. And then segregated ice in this context can cause the formation of thaw lakes, which we see in a lot of different places. But in this area, well, why are they so round? And oh, I clicked away. There we go. So why are these things so round? Um, if we think about what might control the shape of these lakes, we can look up a windrows, and what we see is there's really no dominant wind direction in this area. So though I'm not sure, my hypothesis is that their lakes are very round because there's very homogeneous segregated ice in these sediments, and because there's no dominant wind direction that's driving erosion in a certain direction on these lakes. So with that, we'll cleanse our palettes of the field and move on to ground ice modeling and look at this nice picture for a couple seconds because it's pretty amazing the amount of degradation of permafrost and melt of ground ice we have in this one scene. So when I arrived at the Geological Survey in 2017, my coworker Steve Wolf had already conceptualized this way of potentially modeling ground ice across Canada. And back then it was called the permafrost calculator. So him and my other colleague, Carolyn Duchesne, had kind of worked together on some GIS workflows to allow the prediction of different types of ground ice in the upper 5 meters of permafrost. So in the first couple of years that I was at the Geological Survey, we developed this further, and we had a lot of input from other experts, both both in the permafrost field and the field of superficial geology, who were able to tell us, "Oh yeah, I've mapped this type of material, and in this type of material, you might expect it to be like this, and then therefore you might expect this type of ground ice." And this national scale modeling we did leveraged existing Geological Survey of Canada data set. So in 2019, we published a paper uh, showing new ground ice maps for Canada using this paleogeographic modeling approach, which I'll talk about the approach a little more in subsequent slides. And then we also combined the three ice types that we output in those models into a kind of total ice abundance map, which is called the Ground Ice Map of Canada. And so it shows the estimated percent excess ice volume in the top 5 meters. And we also took a leap and stuck our necks out and applied some uh, estimates, like numeric estimates for each of the classes of ground ice. And we'll come back to some comparisons with those soon. So the modeling, the basis for the modeling is that the materials we have in a place will be related to ground ice conditions. And we needed a data set that we could use as an input layer. And so we kind of made our own, but it's largely based on Fulton's superficial geology at the 1 to 5 million scale for all of Canada. And then we also added from the glacial map of Canada, which is a classic from 1968, large moraine complexes that we know are ice cored from field observations and remote sensing of things like large retrogressive thaw slumps. So we basically stamped on these large moraine complexes onto this data set. And then through conversations with Rod Smith at the Geological Survey, we also parsed out fine and coarse grained till deposits and also colluvial deposits, which was a suggestion from Michel Allard, which is very good. So this is kind of like one of the main inputs into the model. And then we model these three ice types, so relict or buried glacial ice, segregated ice, and wedge ice. And we used other data layers, which include paleovegetation and deglaciation maps. And there's kind of 14 time steps of those. And then we use the glacial map, the maximum marine inundation from the glacial map to melt out relict ice. So if the ocean went on top of somewhere that had buried glacier ice, we assume that that melts out. And then we use the permafrost map to finally melt some stuff out. And it works a little different for the different ice types, but I don't want to get too caught up in the details. So just as I was talking earlier, time matters for the development and the melt of ground ice in permafrost. And this data set by Art Dyke really allows us to get at that in some broad, quite general way because it's, continental scale mapping, but it shows all these different biomes and the evolution of the ice sheet, which allows us to model things over time. And the model really uses a set of if-then rules. So if this happens, then we predict this much ground ice. So that's kind of in basic terms how it works. And so when the 2019 paper came out, we were pretty happy with initial validations comparing where we predicted relict ice and where there's large retrogressive thaw slumps in Northwest Canada. Also for segregated, we saw areas where there's lots of evidence of lots of segregated ice, and these corresponded generally with areas we had mapped as high or medium. And then we compared our results to the ground ice mapping from the Canadian permafrost map, so Hagen-Bottom's map, which was, yeah, we were pretty happy with those comparisons. We did further validation in this open report, which is called the Ground Ice or a Ground Ice Atlas of Canada, where we looked at 31 different areas, and for each area, we kind of wrote a little description of the environment, and we also compared the modeled ground ice abundance to what is actually there in the field, and then discussed why the model works or doesn't work in that area. And one of the key things that came out of this is that the scale of the National Superficial Geology just isn't, it's a very 1 to 5 million scale map, so it's very generalized. It doesn't capture a lot of the superficial geology that is actually on the ground. And then here's just some of the bad news from the national scale mapping, which we also pointed out in our 2019 paper. So this is mapping from the Northwest Territories Thermokarst Collective that Steve Coquel and a lot of others worked on, where they compared, our model output to the distribution of lake lithalsa complexes. So lithalsas are very ice-rich mounds or ridges that are all segregated ice. And what it shows is, well, our model didn't capture that segregated ice very well at all, because the glacial lacustrine sediments that are common throughout that area are not represented at all on the national scale data set. So another sad validation story relates to the Peel Plateau and what I talked about, the unique thermal conditions there. So in the model, the biomes, we use the biomes as a proxy for winter conditions that may be conducive to thermal contraction cracking and the accumulation of ice wedges. Because generally, if you have herb tundra, which is the coldest biome, you are going to have not much snow and you're going to have very cold winter temperatures. And so you expect to have more rapid accumulation of ice wedges in those biomes. But because the biomes actually represent summer growing conditions and not the winter climate, uh, and the winter climate controls the cracking, the thermal contraction cracking regime. On Peel Plateau, where you have these inversions, the model predicts much more wedge ice than there actually is. And so that's a problem that's harder to fix than the superficial geology scale problem. But we can fix it, and we hope to. Now some positive validation. So Tabitha Rahman is doing her PhD work in the Hudson Bay lowlands. And as part of it, she's gone and drilled a bunch of ice wedges there. And she found that they're quite small in terms of width and very shallow. So they're mostly in the top 2 meters of the permafrost there. But when you look at this landscape, you think, wow, there's a lot of ice wedges here because the background picture shows a lot of polygonal terrain. So anyways, she drilled a bunch of ice wedges and then scaled up these observations to the broader area and found that the estimated volume in the top 5 meters of permafrost is 1.2%. And on our legend that we developed for the ground ice map of Canada, we said that negligible is 0 to 2%. And so in this area, it seems like we're more right than some other areas, which we're happy with. And so we produced the national scale model and maps, and we knew a lot of areas that were weak in terms of where the superficial geology was not well represented. So we decided to use much better detailed mapping that we have available, not in all of Canada, but a lot of Canada now, and it keeps the coverage keeps improving. So you can see the difference here. This is an area from Yellowknife and Great Slave Lake north to the Coronation Gulf Coast. And on the left, you see the superficial materials that went into the ground ice map of Canada. And on the right, you see this new compilation we put together using much more detailed superficial geology. And what we find is that it much better represents unconsolidated sediments that might host ground ice. There's just way more representation of that, of those sediment types. And consequently, we model a lot more ground ice and areas of higher abundance that are just not captured in this national scale modeling. And that we published that just last summer. So looking at this difference in superficial geology scale and what the ramifications are for the predicted ground ice contents. We did some validation in that paper as well. And just as a throwback to 6 slides ago, where I showed where we completely missed segregated ice on the national scale mapping. Here we actually capture that segregated ice now in the regional scale mapping, which is B in B here. And then these bar charts just show like where there's mapped lithalsas that there's a couple thousand of them mapped in that area. Where those are mapped, they now correspond to areas of medium or low modeled segregated ice content, which makes much more sense than on the national scale when most of them fell in the none category, and uh, and they almost all fall in glacial lacustrine, where it's mapped as glacial lacustrine sediment. So we're happy with that. And we also did some validation for wedge ice from actually directly on the superficial geology map. Some mappers note ice wedges and others don't. So we have all these points of where there's ice wedges, and we looked at uh, where those fall in terms of the national scale abundance that's modeled versus the regional scale. And it's much better as well, where like we have ice wedges falling in lower medium um, abundance classes rather than none or negligible. And the two bottom charts just show the superficial units where most of those uh, ice wedge polygons were noted. And then the density one shows that standardized by area. And the interesting thing here is in till blanket, there's a lot of ice wedge polygons noted in till blanket, but not many at all based on a density, so count per kilometer squared. And the reason for this is in this Canadian Shield terrain that's rolling, there's a lot of mud boils and there's solifluction sheets on slopes. And those superficial processes, we think, just mask out ice wedge trough. So the downslope movement of material due to solifluction or the circulation due to mud boils is enough to basically make these wedges invisible at the surface from satellite imagery. So what's the point of this? Well, we modeled this corridor because there's a proposed road going from east of Yellowknife to the coast, and it goes through a lot of the mining areas on the Canadian Shield. And so what we showed was that on the right here, if we look at the ground ice contents along this corridor line, we get a lot more useful detail about the predicted abundance of ground ice than both the national scale mapping and the circumpolar map. The circumpolar map, it's basically either medium or low, and there's no detail whatsoever. It also the circumpolar map also thinks that the highest ice contents are in the south of that route, whereas ours is the opposite. So the regional scale model shows lots of ice in the middle and the northern sections. So this type of stuff can be used for, scoping studies or reconnaissance planning. We also modeled the Kavalik region, and we updated the model to include better marine limits that were derived by our colleague at the Geological Survey, Isabel McMartin. And this ground ice mapping is now being used in an actual scoping study for the Kavalik hydrofiber link project, which will bring hydroelectricity and fiber optic cable to communities along the northwest coast of Hudson Bay. There's one other good news story about validation in the Kavalik region. Our colleague Roxanne Frappier from University of Ottawa mapped a ton of ice wedges, and they also did some field measurements of the widths and then assumed a representative depth of cracking. And she has determined that the ground ice content is also negligible in this area, which is what we also model. And on the right, you'll see a picture that shows why this is negligible compared to areas where we have high modeled ground ice content. So in the Kavalik, a lot of the polygons are massive, like 80 or 90 meters across, and the troughs are not super wide. They might be 1, maybe 2 meters. Whereas on Victoria Island or southwest of Cape Bathurst, where we model high wedge ice content, there's much wider troughs, indicating that the wedges below are much wider, and the polygons themselves might be on the order of 10 or 15 meters across. So you just have much more ice in the top 5 meters of the ground than you would somewhere where it's like in the Kavalik. So what's next? We're continuing to improve modeling using new or newer compiled superficial geology in different areas. And thankfully, we've just done the Mackenzie Valley corridor and sort of Arctic coast there. And there's a ton of data we can validate from in these areas. So we're looking forward to doing that. And in terms of field work, which I'll come back to now, we have a project looking at the response of terrain to ice-rich terrain to wildfires that happened in 2023 near Yellowknife. And so this involves coring of lithalsas and other settings. And we're also doing repeat ERT surveys to see the development of thaw after the fires in 2 dimensions underground. So the bottom two images show the electrical resistivity tomography surveys we did this past September at 2 sites. We have boreholes measuring temperature, of course, and moisture content. And then we also have this detailed ground ice information. We're also collaborating with Naomi Short, who's at Natural Resources Canada as well, so the same department as we're in. She's in the remote sensing group, and she's looking at the displacement of the terrain, so the vertical displacements from radar sat constellation mission data. So in between July and August of this past year, she was able to produce this map that shows up to 15 centimeters of subsidence in the burned areas. And in the unburned areas, there's really not much happening. And this coincides with the magnitudes of subsidence due to the melt of ground ice that we got at our measurement sites using the benchmark provided by our instrument casings. So good agreement in the magnitude between the radar sat DINSAR measurements and our field measurements. So in summary, I just wanted to hammer home that sound field and process knowledge is very important for modeling. And if you know more about the field conditions, your modeling will be much better. Validation is key. You should always try to validate your models as rigorously as possible, but it's also commonly lacking, especially when we have broad scale models, and certainly those ones that predict things going 100 years into the future. Those people, nobody's going to be alive to check those. If they do check them, somebody will maybe check them in 100 years, but it certainly won't be us. And then finally, I just wanted to remind everyone to make friends and eat waffles. So with that, I'll say thank you and leave you with this image of that I like. It's from Baffin Island. It shows this river system, and you can see different generations of surfaces and different ice wedge polygon configurations on these different surfaces. So thanks very much.
I'm sure everyone's clapping. We just can't see them. But now, if anyone has any questions, thank you so much, Brendan, for that amazing talk. It's really cool.
No problem. Thanks for having me.
Yeah. Oh my goodness. I also just got over a cold. So anyone feel free to unmute or also type your question in the question box. I see Robert, you raised your hand. Go ahead.
Yeah, that was a great talk, Brendan. Really interesting, and want to thank you for this and all the work you've been doing in this domain. One of the things I want to ask a little bit about is sort of your opinion on the use of. I know I sort of know the answer to this, but in terms of some of these products that are out there, purporting to represent ground ice using, say, machine learning and other techniques, have you done much in the way of assessments of that type of work?
Well, there was one paper that I was the reviewer of that was a global model of ground ice based on machine learning techniques, and the review is public, and I think my response was about 7 or 8 pages of why it's not a good way to do it, particularly how it was done. And that's kind of like why I'm bringing this point of getting to know field conditions before you model, because it's getting easier and easier to produce some graphical output of a model and do very little questioning of it, uh, basing things in reality. And I know Rob from the the geomorphological and sediment settings in Labrador, you've also seen this in other models as well, including the national scale ground ice map of Canada, because of the these small pockets of sediments that can have ground ice, but that aren't represented on national scale mapping. So yeah, like there's a lot of modeling outputs coming out, and many of them are getting published, but a lot of them they're just simply not validated, and a lot of them are incredibly inaccurate based on uh, the knowledge me and others have of conditions in Canada, at least. Yeah.
Thank you
Thank
so
you.
much. Oh, yeah. I also have a question from the Q&A. So about the thaw tube, how can you be sure they are not moving with the ground substance or frost heave?
Uh, well, we're pretty sure of it because uh, they are anchored at about 4 meters and they have a cap on the bottom. So there is a pretty good ad freeze bond. We can also see in the data record sometimes, like we have had ones that have become unanchored. And then you can see the relation between what you measure for thaw penetration, active layer, and ground surface changes. So you can kind of see when something that is not good is happening. But yeah, that is one of the key assumptions, is that we have that expert ability when we're looking at, say, a 30-year record. We have that ability to say, something changed here and it doesn't make sense, and we better throw that one out of the analysis. So yeah, that's about as good an answer I can give for that, I think.
Yeah, thank you. And I guess Natalie also has a question. I don't know if it's the real Natalie though.
Yeah, it's I guess my name changed. So Zach, but great presentation. I had a question about there was a two-handed auger system that I saw in one of the photos. Is
Yeah.
what kind of depths can you get with that system?
So the deepest that uh, I've done and that other people have done is, and this is only under the very best of conditions. Uh, and by very best of conditions, I mean there's no rocks. You're in fine-grained sediments. So around Yellowknife, we've got to like between 7 and 8 meters, but it becomes very heavy and very challenging. Um, in tundra around Ilisarvik, it's hard to get past like a few meters, and there's much more rocks, so you have a higher chance of getting stuck, which I did get stuck a couple times, and it's not fun digging it out.
Has
Um, yeah.
sorry, are you able to use is it only augers or are you able to use coring as well with
So
those systems?
it depends on the gearbox you have. So on the one that I showed the picture of, it's geared to spin very slowly, and that's for augering. But in Svalbard, we used kind of a smaller power head that spun much faster. And with that system, we'd use just contractor concrete core barrels, so like diamond tooth core barrels. And that does a good job in some stuff and not others. Like each system kind of has its strengths and weaknesses. And that one you can get about. I've never gone deeper than a few meters with the one they have in Svalbard. It's also harder to get because you're not cutting with the auger teeth. It's a much tighter tolerance going down the hole. So I think that makes it harder at times. It's also harder to extract the core in the concrete core barrel system. Yeah,
Thank you.
no problem.
Yeah, thank you. Another question online in the Q&A. So thank you for the great talk. I remember a talk of Professor PYRN at UCOP about Ilisarvik, and as far as I remember, he has shown ERT profiles from the growing pingo in the drained lake. However, I have not seen the profiles anywhere afterwards. Do you know about ERT measurements there?
Uh, well, what I can say is there is a growing pingo there because I've stood on it. As far as like Chris has a lot of data that he hasn't published, and if you haven't seen it published, he's probably just still has and hasn't published it. If that answers the question, yeah. I'm sure he's got it somewhere in his back pocket, and maybe eventually he'll publish it. We are working on a paper. I'm working on a paper with Chris right now about Ilisarvik, but it's not about the Pingo growth. So sorry, it's about thermal stuff and active layer.
Yeah, thank you so much, Brendan. We have time for a few more questions if anyone else has anything or comments. Robert, again, yeah, go ahead.
Yeah, I was thinking a little bit about some of the discussion about thaw tubes and just the difficulties and when it comes to measuring sort of active layer thickness, but also I'm thinking in terms of like temperatures at the top of permafrost and stuff like that. Is there any like movement towards recommendations for permafrost monitoring that takes into consideration um, some of the things that you've noted and that others have noted about the difficulties in monitoring features that are subsiding, I guess, over time. Do you know of anything, or is there anything, is there any place that we can point to, or some best practices that you might suggest in terms of those types of dynamic environments?
Yeah, I don't know if anyone's put together like a document specifically on best practice for monitoring. Some of the comm stuff from Alaska, they had a special issue with lots of information on their setup and how they do subsidence there, and I think they've moved towards, you know, measuring subsidence wherever they can and have the resources to in the comm grids. But I don't think there's a document that says like here's how you should monitor, at a active layer site, like a best practice document that I know of.
Thanks, just
But if
curious.
anyone
Yeah.
else knows, I would be curious too.
Maybe there's one coming.
Yeah, maybe. I won't write it though.
Oh, another question. Another comment saying, not a question, but a guidance document would be really useful.
Oh, so does that
So
mean I have to write it?
next
Yeah,
big
that would be a
review.
good activity for like the Canadian Permafrost Association or something. I know there was
Definitely.
guidance documents in the past for like the NSERC Adapt project. They had one for like drilling and some temperature installations, but I don't think it touched on subsidence stuff for active layer purposes. That's the only one I kind of remember recently, at least in Canada.
Yeah,
Yeah.
that would be great.
Yeah, and one of the things with that it just comes to mind that you're talking about is like the whole issue about homogenization of the temperature series then comes into play too, right? Like if you're
Yeah.
talking about, yeah, the way people have boreholes, how we deal with that actually impacts the trends quite a bit, and there's not really any discussion much about homogenization at this point.
Yeah, and we've been kind of getting a lot of our temperature records at the GSC in order in the past few months, and Marcus Phillips has been working a lot on, steps on how to clean it and how to know how to identify different issues with the sensor or the logger. Um, I think we did plan to write something about that stuff. So the kind of cleaning steps we're doing here. Uh, that's just more on the thermal side, not on subsidence or anything. But yeah, I mean, we could add. Yeah, I guess it would be good to get something out there.
Yeah, thank you, Brendan. And I have a question here actually from an undergrad student who really was, I think, inspired by your presentation and just wanted to know, they're asking specifically more about what institutions they could like pursue this kind of research, but maybe I will kind of purposefully misinterpret the question and say, maybe what is some advice you would have for an undergrad student? Because I feel like institution specific is a bit hard to give, but maybe just more general advice if you were an undergrad and you wanted to get
Yeah.
into some of the stuff that you're doing here.
Yeah, I know there was a list on the Canadian Permafrost Association website of different courses offered at different universities in Canada relating to permafrost. So a good thing to do, I think that list is probably still there, or they can this person can email me if they want. And then, yeah, my advice is if you see these professors who are teaching courses about permafrost in Canada, you can email, like people are happy to receive emails from people that are interested and go from there. Like they might have positions they're looking to fill in coming years. And yeah, everyone's pretty friendly in the permafrost community. So if they get an email from an interested student, uh, I'm guessing they'll respond.
Definitely. I think also it's just really great that you're showing initiative and being here. And honestly, some of the names here might be some professors that are interested. But yeah.
Yeah, for sure.
Um, Yeah, but I think that's almost all of the time we have, unless anyone has a last comment or question. Just kind of close this up. So thank you so much, everyone, for coming, and big thank you to Brendan for putting together this presentation and taking the time to give it to everyone. We will be having we'll be having other webinars in the coming months, so be on the lookout for our advertising. But yeah, thank you so much, Brendan. And yeah, thank you and have a great rest of your day. Bye,
Thanks
everyone.
everyone for coming. Bye.